This project basically has application not just to design in a technical smart road, but also to basic introductory high school physics. How? Well, basically, usually high school physics classes start off with motion problems. So we figured we'll design a project that relates to your introductory motion problems and also has an application where the students could actually see that physics could be used for some practical purposes. So the first thing so that's the reason behind the project. Generally, most students that take physics are usually, at least in New York City, tend to be the most exceptional students. We want to try to make physics a little more conducive to students that are not only the brightest in terms of math and science. So what we basically decided to do is to design this highway such that physics become a little more practical. So instead of students basically doing word problems in a high school physics class where they read, instead of students doing just word problems in a high school physics text where they just read a problem and use a formula and solve a problem, we want to actually let the student read the problem and actually see the implication of changing the variables in the equation at hand. They don't have to wait for a lab, etc., to see the results. So in this smart road, we hope that basic motion problems will become easy for the average high school student to understand, and they could see an actual practical application of it.
Oh, do you want to go on to the next slide? Well, one of the rationale, and you're going to be hearing this 4 more times, is to develop a mechatronic system, and presumably a lot of the students are very familiar with this. We wanted to combine the basic elements, which are mechanical parts, the gears, electrical components, and computer chips and computer programming and control. And we think this project, if you go to the next slide, represents this very well. We're using some basic tools from regular physics classes, and we're using them to monitor the motion of a car on the track and control the speed of the car. Of course, these are some of the concepts that Clay mentioned that are usually we begin with them in physics. And this was a way that we could illustrate and demonstrate mechatronics at the same time covering the same curriculum. So we all have time considerations. And we have some of our components. Rather than use photoresistors or IR detectors, we went right with a phototransistor, which has a simple on and off function, whether it gets light or not. And that made the programming much easier to have either a high or low state to send into the microcontroller rather than trying to detect a certain frequency that the IR detector does. This whole premise of our project was to keep it as simple as possible, yet still demonstrate in a valid way the principles of mechatronics and tie in with the physics. Our servo motor is the key to our feedback. When the program senses the car, measures how fast the time it takes to go a fixed distance between the photo gates, it then directs the servo motor to change the potentiometer, which is the speed control for the slot car on the track, reducing it until it's below the speed limit. And this is our circuitry. It's very simple. We have a phototransistor that's hooked up, and it looks for the infrared LED, which is normally on. And when the light is blocked, the current through the transistor stops, and that sends the pin that it's connected to on the basic stamp low. And that's what we're detecting. And if you'll go to the next slide, there's our little pieces of our program. So you can see that we have a loop, and it goes in there, and it waits for one of the detectors, detect 1 to equal 0, and then it slides to a timing routine and waits for the next gate to go to 0. And when it does, it stores the time and prints out and sends it to a velocity count routine. Velocity count routine is rather long because it's overcoming the integer math of the basics 2, so we can get decimal points by using the remainders from our track. We don't want to read this. It's basically what we're talking about now, which we'll go over our problems later. Next. And this is the final product. There's a close-up of the photo gate setup. Again, the circuitry is very simple. We have the IR LED that's always on. Oh, I got it here. And over here, photo transistor. We have an array of 4 of them so that we can get 3 different time intervals.
So
1 to
right
2.
here, located on the track in the side railings here. So there's actually 4 of them, 1, 2, 3, 4. And as the car goes by, they basically turn off. And basically, we measure the time for it to take. We know the distance, so we can measure the velocity from that.
And you can try clicking on the picture. This is a quick video of the track, which we included in the PowerPoint and on the website, if you can get in there. Unfortunately, you can't see the servo motor move. We now like to actually demonstrate it for you. We have to switch connections here a little.
Oh, there was one point where you did.
Keep talking while we're demonstrating. Right?
There was one point which he didn't mention was basically that the reason for the smart highway is that we want to control the speed of the car if the car is going too fast. So we not only want to illustrate basic physics in terms of velocity, acceleration, where the student could actually control on the computer, but we also want to say, hey, if we could basically determine the speed of a car, maybe we could actually prevent the car from speeding up. If the average car has a microcontroller inside of its engine, then we could have sensors on the sides of the roads which basically prevent it from going overboard in terms of speeding. So we have actually done that, and it's shown here. So you'll notice that, and it's controlled by the servo motor in the black.
All right, if you will run the program. No basic standard.
It's not plugged in.
It is plugged in. The lights on. Well, the basic stamp is on.
Okay, there it is.
Okay, now we have fuel input the distance. Now, in class, the students would actually measure the distance
Right.
themselves. It happens to be 35 centimeters.
The distance between the photo gates?
And now you can select the speed. I suggest 42. And the speed.
No, it's an interval. Nah. It actually could be anything.
This display has to be modified slightly because that's not a real number that we're putting in. However, the speed limit I suggest at 45. Now, if you watch.
It could be 46.
Now, try that again. Because we didn't.
You have to run the other program first?
Run it again. Or run. You see the set speed program? Run the set speed program. Along with our package comes 2 diagnostic programs.
Right.
To get this right. There we go. Okay, a limitation of our prototype is the expense to which we went to buy this track, which was very little. Now if you'll run the other program,
Right.
the Smart Road program.
Right. The smart road program basically decreases the speed of the car when it has hit a certain maximum speed.
Okay, so let's try this again, 35. And this time I'll go to 45. And enter a speed limit of 45.
So the car should start speeding up. As you notice, it's starting to speed
And
up.
as it prints out, this 37 is
The velocity
not
of the car is
correct,
shown.
and eventually the
Now reduce the
now the
limit.
speed is being reduced, and the servo motor is slowly cranking down as it monitors, and the speed and the interval is increasing until it goes.
Right.
Now can you reduce the limit?
We can change
Yeah,
the
we can
limit,
change
enter
it.
the
Reduce
distance
the limit.
again, 35.
reduce the highway limit to
Well,
40.
enter a speed of 45 again.
That's the actual speed.
Yeah. And then reduce the limit to 40. So it's now at 33 and it's going to pulse the car and you can see it slowing down each time around. Back down to the speed limit. And now it's reached a steady state.
Let's
speed limit.
run it next time.
Yeah, and it's ready to run again. 35 is the distance.
Set the current speed to 40. Set the limit to 35. So I want to see it slow down even more.
Well, as I said, the numbers are backwards because we have to use count, the actual count value, and what we have to do is change the user interface of our program because
We're based on count rather than
yeah,
actual
it has to
velocity.
be based on count and actual velocity because once you do the division with basic stamp, all you get is an integer answer. And one of the well, the limit is 35 counts, and the program is looking for it to be less than 35 counts.
Right.
When you enter 40 for your speed limit, that's pulsing the servo motor at 800 to give you a speed of about 100 centimeters per second. So like I said, the interface has to be modified so that the numbers you put in will then be changed. But that we ran into difficulties because when you go to divide, you get an integer value, which is not a right count number. So, and that's our